Hi everyone. In this lecture I want to get into some of this concept we've been dancing around for a while about what is a reversible process and what is an irreversible process, and what are the implications of that. So we're transitioning away from the first law of thermodynamics, which is mostly about energy, sort of, where's the heat going, how much work is being done, what's going on with the conservation of energy, into the second law of thermodynamics, which is going to tell us sort of the limits on the efficiency of engines, and it's intimately connected to this idea of things happening only one way, things that are reversible or irreversible. So we need to talk a little bit more about exactly what does it mean for something to be reversible and try to get that concept in our minds first, and then we can move on to the second law of thermodynamics. So here we go. We're going to talk about reversible or irreversible process. This is a joke, which if you don't get it, don't worry about it. So here's where we stand. We've talked about heat engines. We know that a heat engine is something which takes heat from a hot reservoir at temperature TH, uses it to do some work, and then there's some heat left over, which I exhaust into a cold reservoir at temperature TC. The efficiency of the engine is what you get divided by what you pay for it. That's the work you get out, divided by the heat that you extract from the hot reservoir. And then everything we've learned about the first law of thermodynamics, that's basically conservation of energy, is that no energy is created or destroyed by this engine, so that the heat in Q in plus Q out is equal to the work done. And then we talked specifically about this Carnot engine, which was formed from two isothermal processes and two adiabatic processes, and that has an efficiency given by 1 minus Tc over Th. So what I want to do now in this lecture notes is to talk about the meaning of a reversible process and the conditions under which a heat engine is reversible. Okay. So starting to think about high-minded things, when you look around the real world, you notice that there are some things that you never see happen, even though it makes sense that they would be allowed by energy conservation. This is a great play by Sir Tom Stoppard called Arcadia, and the second law of thermodynamics plays a big role in this play, so I highly recommend it for you. The characters are musing, or one of them has noticed something interesting, that they're talking about stirring a bowl of oatmeal up. So suppose you have some jam, which is red, in a bowl of white oatmeal, and you start stirring it. Eventually it gets all mixed up together and it's pink. And then one of them says to the other one, "You can't stir things apart. Time must need runs backwards. And since it will not, we must stir our way onward, mixing as we go, disorder out of disorder, into disorder until pink is complete, unchanging and unchangeable." So basically the idea is I stir the oatmeal up and it becomes pink, but if I stir it the other way, it doesn't unmix itself, right? That's an irreversible process. That's something we never see in the real world, stirring something apart. So in the real world, there are some things which you never see, even though they're permitted by the first law of thermodynamics. So even though they're permitted by energy conservation. And let me give you an example of one of those irreversible processes. Let's take a mass on a spring. So here we go. And this is a system that you all are probably pretty familiar with. It's at rest right now. On the left side, I've got the energy diagram of the mass on the spring. So it's got gravitational potential energy, elastic potential energy. This is the total energy here. And I'm going to bring it down. As I stretch it, the total energy goes up because I put work into it. And then let me let it go. And if I had a real mass in this room, it would oscillate for a while and then it would eventually come to rest. Where did that energy go? I have mechanical energy of kinetic and potential being transformed into thermal energy. So if you watch these bars while that was happening, you saw that the total energy didn't change, but some of the mechanical energy, the kinetic energy, gravitational potential energy, and elastic potential energy is transformed into thermal energy. And that's like the drag force from the air is slowing this thing down, and as a result, the air around this mass would heat up a little bit. Let's watch it one more time. So here we go. Keep your eye on the total energy. You can see that the height of the total energy doesn't change. Energy is conserved, but the I'm creating some thermal energy being converted from mechanical energy. That's something that you see over and over again in the real world. And if you had a mass on a spring in your house and you tried this out, you would see it exactly this way. Something you have never seen is a mass starting at rest here and absorbing some thermal energy from the room and using that to start oscillating up and down. That's kind of the reverse of the process that you're used to seeing. But if you think about it, there's no reason from the point of view of energy that couldn't happen. Why couldn't the room transfer some of its thermal energy into the mass? So the room would cool down and the mass would gain some of that thermal energy. And then why couldn't it just take some of that thermal energy and convert it into mechanical energy and start oscillating up and down? So we see the mass oscillating on a spring eventually coming to rest due to damping. That's where you have the kinetic energy being transformed into thermal energy. But the process we never see would be the reverse of that, take some thermal energy and convert it into kinetic energy. But that somehow never seems to happen in the real world, but there's no reason why it shouldn't by the point of view of energy conservation. Here's a few more examples of irreversible processes. This is from one of my favorite YouTube channels. I'm not sure how well it's going to work on this recording, so let me try to play it, but if it doesn't work well, go ahead and go to YouTube. You can search for this entropic time acapella science, and then you can watch it yourself. I recommend watching the whole thing. I'll just play a little smidgen of it here for you.
Entropic time. Whoa, arrow of entropic. If you made a scrambled egg tonight, there'd be no return to yolk and white. And when it's fried, you can turn it back to raw food. That is the arrow of entropic time.
If you watched that video carefully, you saw this guy had an egg in a pan, and then the egg uncooked itself and then jumped back up into the shell. And obviously that's nothing that you've ever seen in your whole life. You've only seen it go the other way. You crack the egg, you put it into the frying pan, and then you cook it. You never see something uncook, and you never see an egg uncrack and form in its shell again. That's an irreversible process. And the rest of this video is showing a bunch of other irreversible processes. If you watch this video, you can tell that it's being played backwards. So what he did is he filmed it, learned the song backwards, and then reversed the video so that he's singing along with the song being played forwards, but all of the things that you're seeing are going backwards, and you can tell it's being played backwards because it looks weird to you. I want you to keep that in mind, that definition of an irreversible process. So let's use that as an informal definition. An irreversible process is something where if you take a video of it and you play that video backwards and then you show it to someone, they will immediately know that you reversed it because it's something that looks weird to you, it looks wrong. You've never seen it happen that way in the real world. And because you've never seen it happen that way, you know that they must have doctored the video. What does this have to do with engines? Let's think about a simple engine here. So I'm going to take this cycle up at the top right. A to C to B. So I've got isobaric heating here. And then I've got isochoric cooling. And then I've got isothermal compression from B to A. And you can imagine what's going on with a cylinder of gas. So from A to C, I've got some mass on top of this piston, and I put it in contact with a hot reservoir. Heat goes in, so that's the 12,500 joules of heat going in here. And as that goes in, the mass moves upwards. And then once it reaches point C, I lock the pin in place, and I put it in contact with a cold reservoir, so it can cool down. So you can see heat is going out of the gas into the cold reservoir. And then to get it back to its initial state A, I start compressing it. I unlock the pin, and then I start putting masses on one at a time, very slowly, compressing it back down. And as that happens, more heat flows out in that isothermal compression process. I want to think about whether this engine is reversible or not. So let's think about these processes one at a time. So again, this is the isobaric heating process. This is the process at the top there, A to C. So I put the gas on the stove in this cylinder, and heat flows into it, and as a result, the mass goes upward, the temperature inside the gas goes up. Is this a reversible process? Yes or no? Try and take a moment and see if you can think about whether you think this is reversible or not. And here's a hint. Go back to that same definition that I was mentioning. So imagine you take a video of this process. What would you see? You see the mass going up, and you see the temperature of the gas. So if you watch this thermometer, you'd see the temperature of the gas going up, and you could see that the temperature of the gas would be less than the outside temperature. So I've got a thermometer inside and outside, and I see the temperature inside of the gas is going up, and it's less than the temperature outside, which means heat's going in from the outside into the gas. Pause the video and ask yourself if this is a reversible process. So if you showed this video to someone, if you reversed it and showed it to them, what would they see, and would they be able to tell that you doctored the video? Okay, so hopefully you've chosen an answer here. The answer is no, this is not reversible. So think about if you take the video and you reverse it, like in that YouTube video I showed, what would you see? You'd see the mass coming down, that's fine. But then you'd see the temperature inside the gas going down, and you'd see that temperature inside the gas is going to be going down, and it's less than the temperature outside. So it looks to you like heat is going from the cold thing out to the hot thing. And that looks wrong to you. Like if you look at this temperature here, the outside thermometer, if it's bigger than the inside thermometer's temperature, then the inside should heat up. But that's not what you would see in the reversed video. So you can tell this is irreversible because of the way the heat is flowing. Heat, only goes from hot to cold and not the other way around. And so there's a problem. You would be able to tell that this video was doctored. That's an irreversible process. How about a different process? So now let's think about the isothermal heating process. So going back to this engine here, we talked about this step, the isobaric heating, is irreversible, right? If I played that movie backwards with those thermometers, I would be able to tell something was funny going on. How about this one, the B to A, the isothermal compression? What's going on there? I'm putting the masses on one at a time. The whole thing is in contact with a cold reservoir. The temperature of the gas stays constant from B to A. Is that a reversible process or an irreversible process? So here we go again. Imagine filming this process. What would you see? You'd see the masses being added and the piston going down, and the temperature outside equals the temperature inside because it's isothermal, right? So now imagine reversing that video and showing it to someone. What would they see, and would they be able to tell that you reversed it? Go ahead and pause the video and see if you can choose one of these answers. The answer is that this is reversible. Because what would you see? You play the movie backwards, what would you see? You'd see someone taking the masses off. Nothing wrong there. You'd see the piston going up. You get no information from the thermometers because the thermometers are reading the same value the whole time. Isothermal compression. In the one we did previously, I could see that, the thermometer inside was increasing in order to match the thermometer outside, meaning heat was going from hot to cold. And if I played it backwards, I would see the thermometer inside decreasing, even though it's already colder than the one outside, which doesn't make any sense. But in this situation, the two thermometers would read exactly the same value, and I wouldn't be able to tell by looking at the thermometers that something was off about this video. So this is reversible. Let's try to generalize these thoughts. Heat transfer is irreversible, okay? Heat only goes from hot to cold. So if I see, I have a process where I have heat going from hot to cold. If I took a video of that and reversed it, it would look weird to me because I know that heat doesn't go from cold to hot, it only goes from hot to cold. Heat flow is inherently irreversible, okay? And that's a key point. heat only goes from hot to cold and not the other way around. The bigger the temperature difference across which the heat is flowing, the more obvious it is that it's happening and the more irreversible it is. Okay? If I have the temperatures very close to each other in an isothermal process, then I won't be able to tell by looking at the thermometers which way the heat is going. Okay? So the only way to transfer heat reversibly is isothermally. And hopefully you understand that isothermally is an idealization. Heat only goes from a hot temperature to a cold temperature. But if I make those temperature differences really, really, really close to each other, so like 20 degrees and 20.0001 degree, if my thermometers aren't really, really accurate, I wouldn't be able to tell which way the heat was going. Okay. So let me try to summarize and formalize this. To be reversible, a process has to be really slow. So we've talked a lot about the quasi-static approximations in this class. Everything has to be really close to equilibrium the whole time. I can't have any friction or air resistance present, because you know those things are like converting mechanical energy into thermal energy, and you never see the reverse thing happen. And then if you've got some heat transfer, like something hot and something cold in your process, the heat transfer across a finite temperature difference is irreversible. The only way to transfer heat reversibly is isothermally. Let's think about engines to finally sum up here. The Carnot engine is reversible. Why is that? Carnot engine has 2 adiabatic processes and 2 isothermal processes. So where's the heat being transferred in the Carnot engine? It's being transferred in the isothermal process. So from 3 to 4, heat comes in to the gas, and then from 1 to 2, heat goes out of the gas. And that's the isothermal processes where the heat is being transferred. From 4 to 1 and from 3 to 2, that's adiabatic, and there's no heat transfer. Okay? So all of the heat that's being transferred in this engine is being done isothermally, and that is reversible. We said that we could transfer heat across at a constant temperature, and that's reversible. So the Carnot engine is reversible. Instead of going 3 to 4 to 1 to 2, I can go the other way around. 3, 2, 1, 4, back to 3. If I do that in the other order, all that happens is that I take heat in from the cold reservoir when I go from 2 to 1, and then I exhaust heat into the hot reservoir when I go from 4 to 3. Okay? So if I run this cycle once forward and once backwards, I've returned the universe to its initial state. Basically, running it forward, I take some heat out of the hot reservoir and dump it into the cold reservoir. But then if I run it the other way, I just take that heat back out of the cold reservoir and put it in the hot reservoir. Okay? And maybe it's not too hard to understand that if you have 2 heat reservoirs, you got like your oven and your fridge, the only engine which is reversible, which runs between those 2 heat reservoirs, is the Carnot engine. Because the Carnot engine is the only one where all of the heat is transferred isothermally. So I have isothermal here, and then the way to connect the 2 isothermal processes is adiabatic, and there's no heat transfer. If I connect those isothermal processes with any other process, I won't have a reversible engine. I hope that you are now internalizing these key ideas. The first is that, what is an irreversible process? Think about taking a movie of the thing, reversing the movie and showing it to someone. Will they be able to tell that you doctored it? You should know that heat flow is irreversible. Heat goes from hot to cold and not the other way around. But if I transfer the heat across a very small temperature difference, infinitesimally small, then it's approaching reversibility. It's almost reversible. If a heat engine runs between 2 reservoirs, it's reversible only if the heat transfer is done isothermally across that really, really tiny temperature difference. And the only engine which does that is Carnot's engine. So Carnot's engine can be run forwards or backwards. It's a reversible engine. And it's the only reversible engine between 2 heat reservoirs. We'll pick it up there and we'll figure out what are the implications of this. In fact, it's going to have really major implications about what the most efficient engine is between 2 heat reservoirs. And that's where we'll start when we come together in class. Thanks again for your attention. Bye for now, and see you in class.